So I'd first like to talk a little bit about degenerate limits. This is not the title of the talk, but this is the first topic I want to discuss of holomorphic maps. And so what is this? What is this about? Well, if you look at the family of curves, y squared equals x cubed plus t, and you look at this family as t goes to 0, then, well, what do you see? It's somehow in the genus 1 curve, which degenerates as a cuspidal rational curve. That's what the subset of P2 that you get looks like. But if you think about it as a holomorphic map, then when you degenerate a holomorphic map, this one, it's the image of a sphere with a genus 1 curve attached. So okay, so that's basic fact about this Gromov-Witten moduli space, about how curves degenerate.
So the bottom line is the domains.
The domains, yeah, the domains. And I would like to discuss a bit this phenomenon. So let me say, so in algebraic geometry, in algebraic geometry, so the phenomenon I want to discuss is the fact that in this degeneration, at the end, two things are happening. One is that a higher genus curve is being mapped to a point, and the other is that the image of the remaining component is singular. Okay, in algebraic geometry, it's easy to see that these two phenomena somehow always coincide. So if the genus of the image decreases, then there's a singular point. There must be a singular. And that's just because of, for example, constancy of arithmetic genus in flat families. And what I would like to discuss a little bit is what is the analog of this statement in symplectic, in somehow the pseudo-holomorphic curve theory. So in pseudo-holomorphic curve theory, so there's I would like to say that something similar happens, but there's a couple of issues to face. One is that we no longer will have an integrable complex structure, so you can't make any more of this kind of argument about constancy of arithmetic genus. And the other one is that if you actually study the pseudo-holomorphic curve theory, for reasons of trying to achieve transversality, you no longer typically look for actual holomorphic maps, instead, you look for some sort of perturbed holomorphic maps. And if you're going to study maps satisfying this equation, then you've prohibited prohibited singularities from the outset. Okay, so there's no chance that it's going to be 0. Okay, so J naught. So these are two facts that one has to contend with. And so let me say what kind of answer you can give. So nevertheless, something is true. And to formulate it, let me first recall what is the notion of somehow limit that we use in the pseudo-holomorphic curve theory. So, before I get to the statement, let me recall a bit how the notion of limit. Well, if you have a nodal curve, so what does a nodal curve look like to somehow symplectic or differential geometer? Well, you have some part of the curve out there, and then you have a very long, in fact, infinitely long neck. So this is not infinitely long. And then you have another part of the curve out here. And if you have a sequence of curves converging to such a thing, well, what does that look like? Well, the way they like to describe it is they say that you just forget about this part. You somehow forget about this part. And you take a region that looks like this, and you glue it to this region that looks here. And a sequence of curves which converge to this, this kind of infinitely long thing, well, the part where you glue should become somehow longer and longer. So you glue this. This is to get curve near the nodal limit. So having that picture, I can say what is supposed to be true. So nevertheless, given a sequence of curves, converging to a map where there's a higher genus component, and so this one maps to a point, and then the rest, let's say, maps non-trivially. Non-trivial. And I have to make some additional hypotheses, so such that let's go back up here. There's this perturbation, and what I'm going to require, so eventually, this piece is going to a point, and so eventually on that component, that perturbation has to go to 0. And so what I'm going to require is that in my sequence of curves, actually this perturbation is 0 on the part where which will eventually go away. So such that this perturbation equals 0 on somehow a collapsing component.
I think you restrict the perturbations.
Yeah.
You can never keep transfer.
We can discuss that later. I disagree. Well, I mean, you can never achieve transversality at the boundary. I'm not going to care about whether or not that limiting curve. I don't want transversality at this limiting curve. So I agree with you that I will not get transversality there, but I don't want it. So that on this collapsing component, okay, so then what is the conclusion? Then this del bar j, not del bar j, del j of u equals 0 on right here. Okay, so this is the substitute for being. I have no chance of having a singularity there because this thing is not going to be 0, but I can. I am allowed to ask that the holomorphic derivative vanishes. So this is this lemma. So lemma. I won't give the proof of this. It's somehow, well, maybe I'll say one thing about the sort of idea of the proof. The idea is that you have this region where this curve is collapsing into.
Can you tell us what the lemma is before you
Yeah. The lemma is if you have a sequence of curves which converge to someone that looks like this, or the domain is converging to this, the map is converging to something where this piece maps to a point.
Yes.
I demand that the perturbation vanishes on the piece that's going to this part. And the conclusion of the lemma is that on the limiting curve, if I look at the map and I look at what it is right here, its holomorphic derivative is 0.
At a point?
At the point where the other one is attached. Okay. So the proof is supposed to be that, so here is some sort of region where this collapsing curve, yep.
So is psi should also be 0 at that point?
Yeah, psi is like 0 somehow. Well, I mean, when you say what a perturbation is on this broken curve, you're allowed to have it be different things on the two sides. But in this one,
D bar JU is psi at that point.
yeah, that's right. But DJ is somehow is whatever it is. Okay, so I'll explain. I mean, maybe it's not so clear why I'm saying any of this right now, but I'll get to the point in a couple of minutes. So the proof of this is something like the following. If you look at this sort of limiting family, you can just study what the map looks like in this long tube. And the fact that this piece is a higher genus curve sort of forces the winding number of this circle around here to be more than 1. Because if it was just 1, what you would wind up with is a higher genus curve which you could then project to a disk, and like if you do that, the degree had better be more than 1. But since this is more than 1, then on this side it means you have to go somehow more than once around here, which means that the leading order term in this sort of Fourier expansion has to be 0. You have to get to the next term. So that's some idea of why that's true. Okay, so now let me explain. Maybe I do this a bit backwards. Let me explain why on earth we had this discussion.
Tangent space and update dimension were compressed.
What?
Tangent space.
Any dimension. Yeah, any dimension. So it's something I didn't give a title, but I should have at least given my co-author. So this is all joint work with Tobias Akron. So let me now explain why on earth you would care about this kind of fact. So when you study the Gromov-Witten theory, something that is very annoying, at least I find it very annoying, is that if you want to count, let's say, if you want to count holomorphic curves, then the moment you see an embedded holomorphic curve, if you're going to work in a somehow algebraic setting, for example, then you have zillions and zillions more, which come from take whatever curve you began with, attach any component at any point, and map it by a constant map. And such a map will always be holomorphic because you're mapping something to a point. So you can't escape this problem that the moment you see a holomorphic curve, you have tons and tons more contributions. And in fact, and moreover, those contributions are not very interesting. So here's a fact which was proved by Rahul long ago, which is that, so if I have a map to a Calabi-Yau threefold, and this map is an embedding, then the total contribution of these kind of degenerate curves where some pieces are collapsed with image C, so with image C, is given by some particular formula. Is given by e to the u over 2 minus e to the negative u over 2 to the minus Euler characteristic. Okay, there's just some formula. And so there's a huge amount of curves that you have to count, and they're not individual curves. You can like move, you can attach these stuff at any point. So you have higher dimensional moduli space. You have to count them in some way, but the total count of all of them is this formula. And I would not like to do this business of first counting a lot of irrelevant stuff and then rearranging it. I would just like to count that curve by the number 1. And so what I want to explain now is how you can do that. So, okay, so how not to count degenerate curves. A U is the genus counting parameter in Gromov-Witten theory. The statement is, if I were to somehow, so this equals the sum over all curves mapping to C of, the degree of the virtual class times U to the 2G minus 2. 2 minus. Okay, so let me explain how not to count them. Let me first explain, there's one thing you might first try and say. You might say, okay, let's just not count them. And you would run into trouble because, well, you want your Gromov-Witten invariance to be invariant under deformation. And I just showed you a deformation where first you have an honest curve, and then all of a sudden it becomes, in this family now you have a degenerate one. So that's why you should be worried about the fact that I'm saying that you shouldn't count them. Because that looks like a promise that you're not going to get invariance. Actually, there's a second reason how not to count. So the first thing to observe, so now let me restrict attention to the situation of Calabi-Yau 3 geometry. So we look at Calabi-Yau threefolds. The important thing is not actually that it's Calabi-Yau 3, it's that it's index 0 counting problem, but let's just think about Calabi-Yau threefolds. what one does in symplectic geometry typically is you look at this perturbation thing. So in symplectic geometry, it's in the symplectic literature. For example, in this like Ron-Tian literature, you count solutions to by J U equals C. And these solutions in the Calabi-3 geometry, these are just discrete, transversely cut out embedded curves. So someone's going to complain about multiple covers. You would have to worry about multiple covers if you cared about something like this perturbation on a multiple cover being related to the original curve. I don't care about that. So there's no multiple cover issue. So anyway, so in symplectic geometry, when you do the Calabi-3 question, you just count, you just look at a bunch of points, you count them. Now, that fixes this in one sense, which is that you no longer see any of these degenerate curves. And the reason you can no longer somehow just add a bunch of stuff at points is that if this C is really generic, well, it's generic over anything which you try and collapse. And if you've collapsed this thing, this side is definitely 0, and so it can't equal anything else. That is not a solution. And the reason it's not a solution is, what does that do? Well, it just makes all these people you counted separately be completely independent of each other, and you can no longer recognize the fact that they were supposed to come together. So it means you don't see the problem, but you also haven't seen, you've lost a piece of structure which you want. So I would like to try and keep that piece of structure. So what I will do is I'll study perturbations CU which are 0 on collapsed components and generic on non-collapsed components. So when you say it this way, it doesn't really yet make sense because, so I'm going to say it in a more precise way in just 1 second. But that's the idea of what I'm going to try and do. So now let me say more precisely how you do it. If the sphere bubbles, it's not stable.
So maybe we should let the people like me who actually don't see what he's doing. Okay. So what is still going to define what the definition is?
Yeah. Yeah. Okay. So I'm going to work in this polyfold setup. So okay, I have to say a few things about this this polyfold setup. It's not so important, but it's some kind of language which. One has to pick some language, and I picked that one. So there's this Hofer, Wysocki, Zender polyfold setup. And the way this roughly works is that, why do I want to use this? Well, in this setup, there's a space of all maps, all sufficiently regular maps from possibly nodal surface to X. And so and over this space, there's a bundle, which they call W. I think maybe it may have to do with these authors. I'm not 100% certain. That's the notation for it. And this bundle is the bundle which over a map, it's the space of maps from the pullback of the tangent bundle of X. No, I wrote the wrong thing. From T sigma, the pullback of the tangent bundle of X. Okay, that's what its fiber is. And it's the kind of thing which, you know, a section of its bundle is given by del bar. Did I write the wrong thing here?
The section is the space, the fiber is the space of all maps.
The fiber is the space of all linear maps from the of bundles, and so del bar gives you a section.
Which is a Hom and therefore an H.
What?
So you have all three initials.
And the place where you write del bar j equals xi is xi is another section of this. Right?
Maybe anti-promoted anti-complex.
Yeah, maybe anti-complex linear. Yeah, maybe anti-complex linear. And the virtue of this, I mean, the reason I want to take this setup is just to have a place where I can say the words that xi is 0 on maps. And now what I say is if a component of sigma has symplectic area 0, then I put this perturbation 0 on that component. So last time I tried to give a talk about this subject, I tried to say that this was a Sobolev space, and then Kenji objected that there's no such Sobolev space, so I had to learn the word polyform. That's what it is. So now does it make sense what I said? Okay. So now I can explain what to count. So the claim is for generic perturbation xi, which is 0. How to say it? I have to say one more thing first. Sorry. So these, just like for the actual Gromov-Witten moduli spaces, these z's, they come with, you know, genus and marked points. And there are some structure maps. And the most important of these structure maps is the map which glues two marked points to make a node. And there's another one that's kind of important where you forget some marked points. That's like this. And I didn't say, but this W bundle actually it consists. You have to prescribe some kind of regularity. And the regularity, it has the property that if I pull back W along this map, I just get W. And if I pull back along that map, I get a sub-bundle.
So it's on purpose that you forgot this 2 points instead of 1?
You can forget any number you want. No, I mean, it's not on purpose.
But by definition, it would seem to be.
I mean, really, I have to forget all the marked points.
But how does W depend on whether you have a marked point?
Yeah, this is what I didn't say. I didn't explain that this W, you have to look at perturbations, this kind of thing, with certain regularity as you go to the marked points.
Yeah, but W doesn't have any perturbations in it.
The W is a space of such maps, and these maps have to have a certain regularity as you go to the marked points. Like
So
they're,
you can evaluate there?
it's this. I mean, what's let me ask the question. What's really important is that as you go to the node, they have to have a certain regularity, so that you can just, so that this polyfold will be smooth in the appropriate sense.
But then if you forget the mark points, the space should be larger because you no longer impose those regularity conditions.
No, the regularity condition you impose with a marked point is somehow weaker than when it's not there. What? I is the gluing map, F is the forgetting map. F is forgetting map.
You have some component
Yeah,
which is spare,
yeah,
and you have if you forget the mark point is string,
yeah.
then
Yeah, let me not worry about these destabilizing pieces. You have to do something a little bit funny there, and I don't want to discuss that.
it's a very long problem of polyfold.
Yeah, I agree. I agree. There's some issue in the polyfold theory, but there's this Katrin student who wrote something about this topic. This Wolfgang Schmalz. Anyways, but let me not discuss that particular point of the. So anyway, what I want to say is that one wants to choose this Xi so that it's preserved by these maps. So you want Xi with, let's pull back Xi, let's pull back Xi. And one of the things these polyfold people do is they promise you that, or they promise you that if you, you see, if you begin with a Xi here, then you can use it to define a Xi on the nodal locus here, and then you can extend it. So they promise you some formalism and extension of sections.
Compatibility means that it's compatible with forgetting all the mark points, right?
Yeah.
So the location of the mark points is completely irrelevant.
Yeah. I mean, let me say it a little bit differently. How am I going to build this Xi? I'm going to build it from like lowest genus and lowest number of marked points, just pick something there. Then in the next genus, there will be certain boundary components which come from lower genera glued together at marked points. And along that locus, I want to inherit it from before. And then I extend it in any way whatsoever. That's correct. That's correct. I mean that's how you produce such a thing.
What I don't understand is that when you take two of those points and you glue them together,
Yes.
there should have been, I would have assumed,
Yes.
there would have been some condition.
No. It's okay if the perturbations are unrelated.
No, but my concern is that if they're related, if they're actually kind of non-transversal to each other. If they are unrelated, then that's good for you.
No, I'm saying that when I look for solutions of this equation, I can demand that the perturbation there is that those 2 points, the perturbations at those 2 points may just be different. The image will not be a nodal, how to say, it won't look like what you want it to look like.
And of course, you can choose whatever perturbation you want.
Yeah.
When you solve this perturbation, you're going to get a reasonable space.
Yeah, so what definition of this map I? Large I.
I is defined on a subset of a subspace.
Yeah, it's not everywhere. Right?
Yeah. Well, I mean, its image is not everything. Its image is just,
No, I mean, domain. Domain is everywhere?
yeah, I just take the last 2 points, I glue them. Oh, I see. No. Yeah, sorry. You take the ones which map to the same point.
So you have sub-manifold.
Yeah, it's like something of this. So this somehow.
But that subspace may not really be nice.
Would 2 things map to the same point? No, but it's somehow like, it's the pullback of the diagonal inside so it's like virtually nice. Right? It's a pullback of a smooth it's a pullback under evaluation of a smooth submanifold of a manifold.
Yeah, okay, but it could still be some sort of counter set.
That's correct, but somehow like you know, like this space already is not nice.
Sorry, Z is the infinite dimensional space.
Z is the infinite dimensional space. Yeah, okay, let me continue a little bit.
I mean, Z is reasonably nice because it's
Z is reasonably nice, but you know, like solution. I mean, when I take this kind of section, it doesn't have to be nice. But in fact, I think I think this pullback of the diagonal also has to be reasonably nice.
oh, because it's all
All maps. Yeah, I think it has to be reasonably nice.
So I think this overhead viscosity gender give assumptions that you have some sphere component,
Yeah,
which is a source unstable.
yeah.
Then the map should have non-trivial homology classes. Is that assumption you assume or not?
Say again?
So in the books,
Yeah.
they assume the conditions.
Yeah.
Some S2 component,
Yeah,
which is unstable source.
yeah.
Then the map there should be not be homologous to zero.
Yes, I assume that condition.
You assume that.
I mean, how to say? I only look at maps that you could possibly see in a Gromov-Witten moduli space.
Yeah, but then F is not every map.
F is-
Because if you forget the mark point, some component which used to be stable will not get not stable.
Yes, but that's not relevant to this particular issue.
Okay, but F is not stable.
No, but I mean, how to say? I only use F when it's defined because I want the perturbation to be compatible with this pullback when it.
Only subset is.
Yes, but those guys give you a way of extending it. Yeah, that's. I agree. Just when this map is defined, I somehow demand this compatibility. Is it okay? Okay. Okay, so what? So it. Now I want to so consider such a section, such perturbation, and I want to look at this moduli space, which consists of the locus where del bar ju equals xi, and there are no collapsed components. And the point is that, so proposition, this is compact. M is compact. And why? Well, because if I had a family of, so how could it fail to be compact? Well, by Gromov compactness, if I didn't write this last piece, it would be compact. And so how could it fail to be compact? Well, I'd have to have a sequence converging to a collapsed component. I left out the most important part. Hopefully I said it before. I want this xi generic on the non-collapsed components. Okay, so I would have to have a sequence, so proof, a given sequence converging to a map with collapsed component.
So what assumptions? You assume that dimension is zero or something? Or?
Yeah, I mean, I'm working in Calabi-Yau 3.
Okay.
Yeah.
But dimension is zero.
But dimension 0, yeah. And then I'll discuss dimension 1. Okay, so given a sequence converging to a map with collapsed component. No, sorry, Calabi-Yau, no marked points. I mean, the dimension 0 problem.
So G, okay. Is G fixed in this problem or not?
Yeah, G, okay, so fix G, n equals 0, Calabi-Yau third case. C small, and I didn't say it, but C also has to satisfy this hypothesis. That when you make this extension, you do this. Okay, so given a sequence converging to a map with a collapsed component, the limit will have d bar, now no bar, dju equals 0 at some point. And this is not generic.
So what do you mean no collapsed components?
Collapsed component. Collapsed component means there is some irreducible component which maps to something with 0 symplectic area. Okay, so that's the proof of this proposition. That's why this lemma is a useful lemma to have. Is it easier to do this stuff in your technology? This kind of.
I still do not understand your proofs.
Okay. Is your complaint this kind of polyfold issues or something else?
I mean, usually,
Yeah.
when you do the perturbations,
Yeah.
do the perturbation from the boundary to the interior.
Yeah.
And then it's definitely, if the boundary transversality you cannot achieve.
But I don't want transversality of the boundary.
But usually you have a kind of manifold boundary.
Yeah.
You want to find a section which is transversal.
Yeah.
The usual order is first you make it transversal.
I agree, but I'm not. But I'm not going. I mean, I don't care.
I don't know how you can do this without doing this kind of
Wait. Your complaint is you can't extend a section unless it's transverse?
I mean, so you want to prove something transversal in the generic cases.
In the interior.
Yeah, but what you have to do is that, I mean, the interior is non-compact.
Yes.
So if every point in the interior is transversal,
Yeah.
still some zero set diverges to the boundary.
That's correct, yes.
And the usual argument
Yeah.
to avoid it,
Yeah.
you use the transformative.
I agree, but I'm using different argument to avoid it.
Well, you haven't made any argument with transversality. You just proved compact.
That's correct. But I only care about transversality in the interior, which is free more or less.
No, which will be asked about.
No, why? I mean, I have generic perturbations in the interior.
Okay, so maybe it has to do with this extension cost.
Yeah, maybe. Okay, so.
I mean, to a superficial side, it's more like the traditional thing, right? So you go to the boundary, and then you have for these collapsed components, which are probably not regular, but you just forget all about them, and you do a dimension count for the remaining component, which have this extra property, and therefore have negative dimension.
Yeah, that's the argument. Okay, so so I wanted to explain this in the closed case because already in the closed case somehow it's a little bit different than the usual thing. I mean, just to say, now you define the curve count by just counting the number of points in M. You may have to count them with multiplicity or whatever. But and I'll just say without writing that one can conjecture that if you were to make that count and then make this substitution, maybe I'll just write that. So conjecture the sum z to the to G. Let me say this conjecture. Z to the G number of points is M. So G. U to the degree of U at Z equals E to the U over 2 minus E negative U over 2 equals the usual. So it's actually something important. I should have said that Z was always about disconnected curves. So this should be the disconnected Gromov-Witten count. I think if you knew enough comparison results, this would follow from Rahul's calculation.
I'm worried about interaction of the estimates that go include that level over there, and estimates that will go include the expansion over here.
Okay, yeah. Yeah, okay, yeah. Yeah. I agree that's a thing to worry about. Okay, so let me, in the rest of the time, say what this is supposed to be really about, because it's the reason that we were forced to do this was not for this closed Gromov-Witten case, but for the open setting. And in the open Gromov-Witten theory, let me remind you, there's a basic difficulty, which is that you have a curve, and it can degenerate something like this. By this thing pinching off. And in this, in the closed Gromov-Witten theory, when you try and continue the moduli space, you never run into this kind of codimension 1 boundaries, because you're, roughly speaking, doing complex geometry. Anything bad is complex codimension 2. But in the open theory, you really face this kind of issue. And historically, people try and deal with it by saying that there's lots of ways of dealing with it, with these bounding chains and so on. And it can be thought of more or less as finding some way to continue the moduli space. With Tobias, we have a different proposal for how to deal with this, which is that if you look at that degeneration, well, there's another curve which is also mapping to this one, namely a cylinder. There's a cylinder which maps here, which just maps as a somehow immersion. And if you look at this kind of degeneration where this if you look at this in the moduli where this curve has degenerated to this one, then there's another family which also has this image. So in this family, I'm immersing a cylinder at this moment, and at the rest of the moments, it's somehow some other cylinder. Okay, so I'm mapping, just to be clear about what I'm doing, I'm mapping curves to a Calabi-Yau threefold with a holomorphic with a Lagrangian. And this is something which, this is a phenomenon which you can see. And the proposal of, that Tobias and I made is that you can use this second family to cure the first one. And the way you do that is that you count the curves by the class of their boundaries, and you always count them by the class of their boundaries. But now we're going to count them by the class of the boundaries in the skein module. So the proposal is that you count curves by the class of their boundaries in the skein module of the Lagrangian. And the skein module, what is it? Well, it's curves, one real dimensional curves in L, so formal linear combinations of curves in L, modulo two relations, one which looks like this, another one, I should put some A's, A inverse. And also you should say what the unknot goes to. So A minus A inverse is Z times the unknot. So modulo these relations. And how does that fix the problem? Well, if you look at the boundaries of these curves and how they change, well, the boundary of this curve maybe looks like that. Whereas the boundary of these two curves, one will look like this, and one will look like this. The boundary lives in this three-dimensional manifold. If I fix attention on a ball around this point, and look how they, they're going to be basically the same except for a ball around that point. And I look how they look like in that ball. Then one will look like this, one will look like that, one will look like the other thing. I mean, just think about this and how you can deform it. If you deform the immersion, then these are the two possibilities. Whereas if you deform it as something cut out as an equation, it deforms like that. It's something you can check by writing equations. So okay, so this was the proposal. And there's one aspect of this proposal which is slightly subtle, which is that you can worry that there's another phenomenon. Maybe let me tell you one other phenomenon which does happen, which is that other phenomenon which does happen is that you can have, so here's Lagrangian, you can have something which ends on this Lagrangian can degenerate to something which somehow ends on it only at a point. That circle could shrink to size 0. But the cure is kind of similar. There's another family where there's someone who does not quite meet this Lagrangian, then is accidentally touching it for a moment, and then goes to the other side somehow. I mean, other side's a little bit confusing because it's a two-dimensional thing, a three-dimensional thing. Anyway, so you have a similar story to this one, and that has to do with the second equation. Okay, so, but there's one other thing that you might be worried would happen, and which would happen vector space.
Vector space. So the traditional counting is done labeled by cohomology.
Yeah.
So what's the relation between this?
Well, okay. I should. When you say the traditional counting is done, no one knows how to define the open Gromov-Witten theory and how genus. So there's no traditional counting which is done. But people in the past thought that maybe you should do it labeled by cohomology. So yeah. And the proposed answer is that no, you shouldn't do that. And one reason you might believe this proposed answer a priori is that Witten tells you that the open Gromov-Witten theory should be related in a certain way to the Chern-Simons theory. And if you think very carefully about what he says, this is how you should count. Well, he doesn't exactly say that, but somehow, I mean, there's something actually which is different about this than what Witten tells you to do, which is that Witten tells you that it should be related to the perturbative Chern-Simons theory. And I'm telling you it's related to the non-perturbative Chern-Simons theory. And the difference between those things, it actually has to do with this, this not counting of collapsed components. Because in the perturbative Chern-Simons theory, you will see, just in terms of which variables you use, you will see this somehow the counting variable for Gromov-Witten theory. But in the non-perturbative Chern-Simons theory, in what you would usually think about as like Jones polynomial or whatever, you see a different variable, which is e to that one, which is closer to this thing. I'm not exactly sure. Yeah, I somehow, it's a question for physicists what exactly this is.
Maybe my question is to you. So what field theory is it for which the closed string is this string? Some of the things you've named? It looks like the sulfur version of
Yeah.
I'm not sure.
Yeah, it's somehow closer to counting M-branes than the more conventional approach, but it's not exactly counting M-branes because of this perturbation.
Yeah, I'm not worried about the curve. I'm worried. I just would like to know what the real curves of the three manifold, what that vector space is.
That vector space is the space of defects in Chern-Simons theory. But and to say that, you have to say non-perturbative Chern-Simons theory.
Yeah, no, I see.
Okay, so I just wanted to explain in my last minute how this approach, like what problem it would run into, which this is supposed to solve, and the problem that one worries about is that you have some part of the curve, like this part, which is collapsing to a point. Because I don't have a skein picture to cure this problem. And so I have to remove it in some other way. And the way we prefer to remove it is to set up set up this theory in the open case. So I'll stop there.
Just one more point. I think probably okay for the case, but you
Yeah.
there might happen that this task C on the support of this C. I mean on the main part of the support of C.
The cusp occurs.
And we have this S2
Yeah.
and this toroid, right?
Yeah.
Toroid shrinks the point.
Yeah.
But then on the main part,
Yeah.
you use this C to perturb this D bar.
Yeah.
And then you want to show that kind of this point should be have a differential with 0
Yeah,
and
yeah.
decrease the dimensions.
Yeah, yeah.
But in the case where this happens on a support of C,
Yeah.
you're in trouble, I think, right? Because it's not from the curve on this side.
No, but I'm not saying that there's actually a singularity. I'm saying that the holomorphic differential is 0.
So that this lemma holds the C has a support on the main part, but it sits on this singular point.
I mean, but the point's not actually singular. It just has holomorphic differential 0 and non-holomorphic part.
But usually, probably it's okay, but usually when we do this perturbation business,
Yeah,
we require that this perturbations
yeah.
has no support on this double point.
Ah,
That might be
okay.
simplifying assumptions,
I see.
but that's technical point.
Okay.
But I think this border case is okay,
Okay.
because you can assume C is supported integer.
Yeah, that's right. Yeah. The border case is easier for
In that
this.
sense, yes.
Yeah, it's easier.
Okay, thank you again.